Hello, my name is John Kramer, and I'm here to explain a innovative way of diving. Let's start with a brief history of diving. Diving can be traced back thousands of years ago when it was used to harvest minerals such as sea fish, sponges, coral, and pearls. In 332 BC, Alexander the Great was the first to employ diving tactics into his military purposes. And the earliest diving designs that resemble modern diving technology came about in the early 16th and 17th centuries. The diving bell, as seen in the upper picture, began use in 1531, and divers also started to use surface supply diving, such as the picture below, but quickly realized you cannot breathe through a tube up to the surface, and a pump was required, which wasn't available until the early 1800s. As humans began to dive deeper and longer, physiological problems and constraints began to arise, such as air supply, decompression sickness, and gas mixtures. In regards to air supply, a human requires between 10 and 90 liters per minute of volume of breathing gas, depending on their workload. And this standard volume, will increase dramatically as pressure increases, thus density will increase as well. And decompression sickness occurs when a diver has been breathing compressed air or gas and begins to ascend rapidly. And with regards to gas mixtures, the partial pressure of each gas must remain within a constraint. Decompression sickness occurs when inert gases from breathing mix dissolve into the body's tissues and blood when breathing pressurized gas. Then if a diver begins to ascend or decompress too rapidly, these gases will form bubbles, which can block blood vessels and damage cells. To combat this, divers execute decompression stops, which allows their bodies to off-gas. However, this time required for decompression stops increases exponentially with added depth or duration. For example, this could last several hours for a simple 10-minute dive to 200 feet or more. When looking at gas mixtures that divers breathe, they must maintain a partial pressure of oxygen between 0.16 and 1.3 atmospheres. This maximum value is decreased to 0.5 for extended periods of time. With too little partial pressure of oxygen, the diver will begin to experience hypoxia, too high, and the diver will experience oxygen toxicity. The diver must also make sure their partial pressure of CO2 is less than 0.015 atmospheres, and their partial pressure of nitrogen is within a reasonable limit, or else nitrogen narcosis will begin. This has a similar effect to alcohol, and its effect can vary from diver to diver, but is generally said to occur around a partial pressure of 3 atmospheres. As humans wanted to dive deeper and for longer periods of time, new innovative ways of diving must be developed. Several challenges and requirements for these new concepts of diving are that they must allow the diver to dive deeper and for longer periods of time, maintain conditions which satisfy all of the diver's physiological needs, and provide a controlled environment to maximize safety. Below is a figure illustrating several concepts to solve this problem. The solution of this problem would be driven largely by four stakeholders, including researchers, salvagers, the military, and the largest stakeholder, the oil industry. As shown in the picture to the right is an oil rig under maintenance from a diver. Several solutions to this challenge have been explored, such as just simple standard scuba or surface supply divers, which require large decompression penalties, as mentioned earlier, up to several hours, and requires the use of multiple gas mixes as the partial pressures need to remain within their safety limits. Another solution that has been explored is an atmospheric diving suit, as seen in the picture to the right. In this, the diver would remain at 1 atmosphere and therefore would not have to experience any decompression penalties upon surfacing. But several issues with this include the extreme bulkiness and limited mobility. Another solution to this issue arose in the 1960s with the development of saturation diving. In this method, the divers are kept compressed throughout work, sleep, and play, thus only requiring 1 decompression penalty at the end of multiple dives. The idea is based on the fact that once a diver's tissue has absorbed the maximum partial pressure of gas, there is no added decompression penalty with a farther exposure in duration. Therefore, if a diver were to live at the pressure, they would only have to execute 1 decompression cycle. The initial concepts of saturation diving consisted of underwater habitats, which began during the 1960s with the U.S. Navy's development and conduction of Sealab experiments. With this concept, the divers would live in an underwater structure at pressure and then be able to swim out, conduct their work, and then swim back within the structure. However, several problems arose with this concept, mostly due to the fact that support and communication was so far away that with any issue that arose, help could not get there quick enough. Due to these issues, saturation diving evolved into a new concept consisting of a surface chamber with a diving bell. In this concept, divers would live in hyperbaric chambers and then be transported to and from the surface within a diving bell. A picture of this is shown to the right. Due to these issues, saturation diving evolved into a new concept consisting of a surface chamber with a diving bell, as shown in the picture to the right. In this concept, divers would live in hyperbaric chambers at the surface and then be transported down to the seafloor bed in a pressurized diving bell. And then they could exit the diving bell, execute their work, return to the diving bell, then return to the surface and their living quarters. Most of these systems were implemented on sea vessels and ships. Therefore, there was a need for life rafts in the event of an emergency, due to the fact that the divers are living under pressure and cannot simply exit the hyperbaric chamber, or else they would experience extreme decompression sicknesses and illnesses. They must have a dedicated life raft, as shown in the picture above their hyperbaric chambers, in which is equalized pressure to their hyperbaric chamber that they can crawl into, and the life raft would slowly equalize pressure in the event of an emergency. However, this is rarely, if not ever, been used. Several benefits of this innovative method of diving include that it allows the divers to work up to weeks with multiple dives for as long as needed, with only one controlled decompression cycle at the end. Their resources, such as food, water, can be given to them easily as they spend most of their time on the ship at the surface. And also, due to this, close monitoring and communication can be done. One interesting side effect of this method, however, is due to the fact that these divers are at such high pressures. If you recall the effect of nitrogen narcosis, nitrogen has to be removed from the gas mix, and instead they use a helium and oxygen mixture as their breathing gas. This results in a Donald Duck effect to their voices, which can cause it quite hard to understand each other at times. But over time, they begin to comprehend this new language, so to speak, that they are all speaking. But this has also led to the development of new technologies, such as voice translators, to allow their communication to be done more effectively and smoothly as normal. From the depths of the ocean to outer space, an interesting phenomenon is realized that we are all, in fact, saturation divers, except typically just at 1 atmosphere. Our body tissues have equalized partial pressures of nitrogen from the air that we breathe and within the tissues themselves. This is realized in outer space because the spacesuit is at 4.3 atmospheres absolute, and in order for an astronaut to get in the suit and execute a spacewalk, they must go through a 4-hour decompression cycle from 1 atmosphere to this 4.3 psi. Thank you, and here are my resources.